But I wanted to bring to your attention today that we have a very important guest coming in. Her name is Lorena Mesa. She's going to be coming in from she's a GitHub data engineer, which is somehow, it's written here. And she's also very active in Python software development. She's also part of the Python Software Foundation. Now, she's coming to Zoom all the way to our class from, I think she's coming from Chicago. And so she's going to come and deliver a message on basically preparing responsible technology. Like, how do you create responsible technology? Now, we're probably all thinking, well, what do we care about that? I mean, why do we need to know about responsible technology? I mean, isn't all technology in some ways responsible because the people who use this software are in themselves responsible? Well, no, that doesn't always mean that because the technology out there is available that it's going to be used responsibly. So, for instance, you can think of, well, I mean, any social networking technology which exists. In fact, if you think about Facebook, perhaps, maybe when Facebook was being developed, perhaps nobody back then was thinking about cyber stalking or, for instance, the potential of people to feel depressed or neglected because they don't have the same exciting lives that they see that their friends have. But remember, their friends are only publishing photos of the highlights of their life. And so when we see the photos of other people, we tend to think that those people have terrific lives and that our lives are not the same. That's really far from the truth. The truth is that we all have ups and downs. We all have good days and bad days, and we all have times in our life where we're feeling really, really happy, and sometimes in our lives where we feel really, really sad. These things happen all the time. But the thing is, though, that when you use some of these social networking programs, maybe even TikTok, you only see the good sides of people's lives, and so then you begin to think that perhaps your life isn't as wonderful as it could be, and therefore you get these. You may begin to feel sad, depressed. These are actual problems that happen as a result of using some of these social networks, the social networking technologies. And so this is it's against the ethics, I would say, of software when you creating software that makes people feel bad about themselves, or when you make people feel that that they have holes in their lives. And so what I'm saying is that the technology that we produce and the uses that it has actually have a very big mark on the kinds of lives that we have. I mean, the way that we use this technology could actually inform us, or we believe that it informs us, about the kinds of lives that we live. But I would argue that that's not the case. That's not these are the technology that we have, or the social life that we believe that we have online is not really who we are. We are better than that. Anyhow, what I'm saying is that we have a speaker here, Lorena Mesa, who's coming to talk about those kinds of ideas when, for instance, you're creating a technology. How is that technology to be used so that it's ethical, which means that it's doing no one any harm, and also it's perhaps even making the world a better place. And so her talk is going to be just about being responsible when you're creating technology. Can you create a technology where, for instance, you can think about all the potential uses that it may have, so that you can create a technology which isn't injurious, which doesn't injure anybody to use? Anyhow, I think that that's going to be a really, really good talk, and I'm really, really looking forward to seeing this. Now, when you come to this technology, responsible technology talk, which is today at November 17th, which is today at 6 p.m. our time, Eastern Standard Time, you will have, I'll put out a message on Slack just before the talk, really asking you to answer a question or something, and when you hand that in, you'll get some extra credit for being there. I haven't decided exactly how you'll hand this in. I'm thinking that you'll probably have to use your practicals repository, but I'll send out the instructions closer to the time. So please do check your Slack, or even if you certainly check your Slack after the talk, and I'll tell you how you can submit, or what the question was that I'd like you to do. But basically, though, I want to make sure that you actually were at this talk. So that's today at 6, and then tomorrow on the 19th, or not tomorrow, the following day on the 19th, 12:30 to 1:30, we have information session. We have information session on careers, GitHub, and the open source community. This talk, I think, will be just terrific, because I can think of many people who would love to get in on how do you start an open source community project? How do you get into GitHub? How can you have a career where you're developing software? I think that we all like developing. Well, I'm talking from the computer science point of view here, but most of us like developing software, and so I think that how can you find a career where you're developing software? That is actually really that'd be a really good conversation to have to find out how you can kind of live the dream in some ways here, and it's well paid, I believe. Do you have a question, sir?
Yeah.
How do you sign up to go to this thing? You have to go to this RSVP link, and then you will receive a message. I guess it's a Google form, and you sign up for this. You send this link here, and then you'll get an email with the Zoom link after that time. So it should be really exciting. She's a wonderful speaker, a really excellent speaker, and so I do ask that everyone, even if there were not any extra credits, still come because it's just fun. It's just amazing stuff to hear about these kinds of things. Anyway, I'll see you there. What I would like to do today, though, is I'd like to go back to these slides here, where we're talking about this lab that we were working on. I believe it's like what, lab 5 or something, where we're talking about the vaccines. And I wanted everyone here to know kind of like about how vaccines work in terms of like how do you determine whether they're actually, what's called the efficacy of these vaccines. In other words, are they doing what they're supposed to be doing? Are we just injecting people with a bunch of water, which doesn't do anything, or is it actually something that has some therapeutic? Is there some therapeutic result? In other words, we're actually able to keep certain types of viruses at bay here. And so, in the lab that we were working with, we were looking at vaccines for measles, mumps, hepatitis B, and some other nasty viruses. Now, these are all terrible viruses which were around in the 60s and before, and many parents would be very wafraid to let their children outside and play in playgrounds with other kids who may have had these same kinds of who may have had measles, mumps, and hepatitis B. This is very much the same thing that we're going through today when we're thinking about gathering out in open doors, or we're thinking about I'd rather be outside gathering with people than inside, because we're all afraid of the COVID-19 virus. But imagine, for instance, having every day for your entire childhood, listening to your parents talking about how measles, mumps, and hepatitis B are going to come and get you, unless, of course, you do exactly what they say. That becomes exhausting, and people get worn out, just as we're beginning to get worn out now from the virus. We have to keep going, though. We have to keep going. Be strong. Anyway, so what I'm trying to say, though, is like when you're giving someone a vaccine, you're actually giving them some kind of a system of stopping the virus. And so one thing I was talking about last time, and just to get myself caught up, is that this is a graph of the years up to from 60s to 70s up to 2005, where you're giving people vaccines. Now, the actual line on here is a line which was created after data points, and the data points were talking about the cases of mumps. Mumps is a terrible virus which a lot of children could get, which could be life-threatening. It's just a virus. Anyhow, so you have this, you have mumps, but the thing is, this line here is not actually this is not the data. The data wasn't plotted. This is just a smooth line of the data points that we would have had. But you can see that every time at each of these important points here, we have the licensure of non-violent, monovalent mumps, vax, and then some licensure of other things. These are all kinds of introductions of types of vaccines. And you can see that when those vaccines have been given out, the trend in the data has gone down. So I'm looking at, for instance, 1970, like around that dotted line there. The lines, or the graph line, was going to go up, and then we had this licensure, which means that something was done, and so then it changed the trend. And so what we're doing now at this lab is we're studying the trend changes that result as in function of the use of vaccines. Let me just say that this is some other data. Before we actually do the actual analyses here, this is the data that that we have which suggests that these vaccines are actually working. So for instance, here we have smallpox, diphtheria, pertussis, and some other things. And if we have the 20th century annual morbidity, these are like your traditional trends in the cases that you typically get. But you can see though that in 2010, the cases have really gone down. In some cases we have zeros, and in other cases the numbers have become very, very, very small. This suggests that something is preventing those viruses from continuing to infect people. There's a decrease involved, and that's exactly what we want. In order for us to avoid pandemics and epidemics and things, you need to decrease the number of infections that you get. And in order to do that, you have to have some kind of other, in our case, we're trying socially distancing, we're using masks, we're washing our hands every 20 minutes or whatever it is, but we're making sure that we live clean lifestyles, and that helps to deplete the virus. It stops the virus from infecting us. It makes the chances that the virus could infect us fewer. If the virus is always being washed off our hands, if we're preventing our breaths from transferring to others here, then it prevents the virus from spreading. But vaccines actually are a good way of preventing the vaccine or preventing the virus from spreading, because they actually train your body in some way to prevent that vaccine, or prevent I keep saying vaccine, I mean virus, but prevent the virus from actually spreading. And so this is actual like formal data that says that yes, the vaccine appears to be working because we have fewer cases now than we did traditionally. So this is where you need to start actually looking at the data more carefully. Remember, this is just a table of numbers. It doesn't tell you anything about really what's going on. It doesn't tell you, this is what I don't like about this table. I mean, I like this table, but I don't like this table. I like the table that it talks about, for instance, in 2010, the cases have gone down. That's a good thing. It shows us the cases are not the same. They've gone down from what they were. But it doesn't really tell us when those cases went down. And so if you're trying to decide whether is it socially distancing, supposing they were working with socially distancing when they're talking about mumps and measles, is that what made these cases go down? Was it washing hands? What exactly was it that made these cases go down? You won't find that information really here. And so you have to go into a deeper study. And this is really where our lab picks up, where, for instance, we have all this data. In fact, this is the code when I take a stab at the lab. I know that I've repeated myself. We went through some of this stuff on Thursday, but I don't really remember where we ended up, so I'll just go through it briefly over here. But we have all this code, and the code, actually you'll see that we have this information here, which is this US contagious diseases. This is the data that we actually have built into R, which contains mumps, measles, Hep A, B, and C, I think, and some other really nasty viruses that used to plague children and even young adults. Well, actually even adults themselves, back seemingly, well, since forever. Like they were always being plagued by these viruses. Anyhow, but this is a particularly rewarding plot, because what we see now is that you'll see that this I'm putting a V line here, or a GMV line, which really says make a red line at the X value where X is equal to 1965. 1965 is significant in vaccines for mumps and measles, in that was when it was the projects became mainstream, where people, children specifically, were getting their vaccine shots. And so these points that we see in this plot are actually cases. You can see in the 1930s, 40s, 50s, 60s, you can see that those cases are on the left-hand side. But we had different years, but we had many different cases. The cases were very high in some cases. In some cases, for instance, I'm looking at just before 1940. There's an outlier at the very, very top, just underneath where I'm right now. But you see that there are some outliers which are actually very, very high. These were very bad years. I mean, of course, to find out why the number of cases was so high, the count of cases was so high, you'd have to actually go back to 1940. And in fact, in this case, this might be like 1939 or something. But find out what was going on to make so many people sick. But each of these points, though, represents it represents human suffering, people getting sick. Now, after the big red intercept at 1965, that's when the vaccines began to take hold. And those vaccines are kind of, we can see that the vaccines have prevented these crazy cases, and now they're becoming more controlled. Now, you haven't stamped out the cases of vaccine just yet, or sorry, the cases of the virus yet. You haven't stamped them out. But many of the cases you have, many of the cases which were like really, really elevated and really high, are no longer there. And on the right-hand side, from like 1964 and onwards, you can see that the cases are very, very few. Well, relatively. But you always have cases. And the reason for that is because some people are afraid of vaccines. And not that this lab is designed to make you take your vaccine, but this lab is designed to kind of show you that vaccines are not dangerous and that they actually will help you. I actually think that vaccines are a very good idea. And I think that there's the reason why many people don't like vaccines was because of a paper which was actually mentioned in this lab where you had to read it, and that was your ethical question, where you're reading about, for instance, how it was suggested by one infamous researcher who has actually now been barred from research, but Andrew Wakefield was saying that you have this this tendency to get Alzheimer's, or not Alzheimer's, to get trisomy or Asperger's syndrome or autism from taking vaccines. And so autism is actually, there's no evidence of getting autism from vaccines. His study was using 14 people and they were cherry picked. And even then, some of the data wasn't that conclusive. And the people he worked with actually pulled their names from it, realizing that, okay, this is serious now. Maybe the joke is up. Maybe we shouldn't be a part of this paper. But still, people did believe it. And then now everyone seems to, not everyone, but a lot of people seem to think that vaccines cause autism. And that's really not the truth. Many, many, many research projects have come out to refute it. But still, on the left-hand side of this graph here, there are still a population of people who are getting sick from measles and mumps and hepatitis A and B and all those things because they refuse to be vaccinated, because they still think that autism is going to come to them if they are vaccinated, which is not the case. There's so many different things to read about this. Anyhow, I put my code here so that you can see what's going on. In the data set, we have this U.S. contagious diseases. We're looking at measles in this case. You can see that we're only looking at the measles for this lab just because it helps to reduce the focus. I mean, ideally, you could do the same study for every single ailment which exists in this data set. In this case, we just use measles because it shuts things down a bit. But Hep A, B, and C is in there. You have the mumps. You have seemingly a bunch of things you can choose from. Now, this rate over here, this is significant. The number itself might be ugly and not very mathematically interesting to look at, but it does combine, for instance, a count, a population, over 100,000 people, and some kind of time. It combines all three or all four of these main elements into one nice number. And so that rate is really what we're looking at when we're trying to figure out the rates of infections per population in 100,000 of a community of 100,000. And so that is why we have this, we use this rate. And I believe that I actually gave you the equation in your lab to put this together, but this is your equation you could use. Now, there are probably other ways you could write a rate. You could probably figure out some other system that you're using to combine some of these numbers together. But the way that this is put together is a kind of a frequency type of format here, where you have the proportion over the total it's a smaller number than if you're just multiplying all these things together. But you could probably still do that if you wanted to. But I still like this idea because when you have this over time business, you have this you have this number here over time, which suggests you have a kind of a I don't know, you actually are working with a rate, something happening over time. Anyhow, so then the next thing that the lab is doing, it says remove Alaska and remove Hawaii. And for this, I use the filter command. That's the filter. We actually hit the filter command when we were working with in our slides here. We actually have the filter command, and we use that to actually pull out rows of data from our big data set. And so I'm pulling out, for instance, all states as long as the state does not equal Alaska and as long as the state does not equal Hawaii. And the reason for that is because Alaska and Hawaii became states lastly, the data actually began before they were states. And so adding them into the data set having them not added and then having the data kind of begin and then having them added just made everything seem a little bit unusual. But that was just part of the instructions of the lab here, just because I wanted to keep everything kind of together. Now, the plot was this. I believe that you've seen this plot already. In fact, the plot should be here. And this is the most telling plot. In fact, I think that when researchers first saw this plot, and we're not the only ones to have seen this thing, but when researchers first saw this plot, though, they were sure that that was the beginning of a great future in vaccines. They were able to see that, okay, so the vaccine came out in 1963, and it took some time. Perhaps this part of the time after the red line, there were still some cases. They were going down, but there's still some cases, and maybe that was just because of some populations either had not received their vaccine, or, for instance, maybe they just resisted taking their vaccine for some reason. But then after a while, you can see that maybe toward 1970, maybe 1968, 1970, populations actually, or the cases of these mumps, or is it measles? Yeah, cases of the measles actually did go down significantly. And so that means that something worked. And I would say that this is just a logistical problem. This is the same problem that we have today, in fact, when we're thinking about how do we give out the vaccine for COVID-19 to all the millions and millions of people that we share our country with and the world. How does everyone get a dosage of this vaccine? It's a very difficult problem, because that means that you have to actually arrange to have that person with some kind of a specialist or a nurse or a doctor, somebody in the same place at the same time with the right amounts of chemicals or the right amounts of vaccines and the equipment that they need. There's a lot of moving parts. I know that doesn't sound like much when you're thinking about just one person, one doctor, and one vaccine dose. But if you think about that in terms of millions and millions of people, that's actually quite a different task. And furthermore, one of the things that we have to worry about today, which is quite difficult, is that our vaccines have to be kept at almost super frozen temperatures to make sure that they don't degrade. And so that means that you have to make sure that people come to us to a place at a specific time when the vaccine is ready to be given, and it has to be delivered to that place at a certain time. So what I'm saying is all of this has to be done while it's super cooled and plugged in, and you can't have any power failures. So there's a lot of moving parts, and so it becomes very, very difficult. And so I would say that maybe after this first line here in 1963, there were some logistical problems that they had to overcome before everyone could be given this vaccine. Now, the next thing that I have in this lab is we work with this data set here called CaliFocus. CaliFocus is we just chose California. You could have used any state. I think California was chosen in this case because California seems to be a good kind of representation of the rest of the countries. And again, what we're doing is we're looking at, for instance, the intercepts at 1963, assuming that in California they were all given the vaccine just like the rest of the country. And so we're seeing, for instance, what does the California landscape look like? And you can see that the data here is less, but the trend is still the same. So going back here, in this data, this is all from all 50 states, or all 48 states. Inside here we have California data, and here we're just looking directly just at the California data. Now this is actually done quite a lot. This is like a sampling, if you will, of your data set. And the reason why you do this is because sometimes if you're working with like many hundreds of thousands of points, it might take some time for your computer to actually do that work, or maybe, for instance, you might get lost in the noise, or maybe you don't see what's going on. And so if you choose some representative of your data set, like a sample size or sample set, then sometimes what you learn from that can actually be extrapolated to the rest of the set, which we can do right here. You might try, like later on, to see whether if you change from, rather than using California, try using Pennsylvania or any other state and seeing whether you still get a graph that looks like this. Now, I would wager that you would, because here we're looking at all states together, and we can see on the right-hand side that on the right-hand side of this line, of the red line, that the cases are coming down. And so I would say that every state is going to show that kind of trend, just in a different way. It looks slightly different, but it's still the same trend. Anyhow, So what I'm trying to say is that when you're working with some of this data here, one of the things that I ran into when looking at this was that there's some transformations that have to be done to actually help me to kind of see what's going on in the data. Now, a transformation, I didn't have the transformation done in the lab though, because that was this extra stuff, and by the nature of this class this semester, we just didn't have time to actually go into transformation study. But actually, a transformation is when you're taking the data and you are moving it into you're basically converting it in a linear fashion or some other fashion into a different kind of, you're putting the same data on a different playing field so that you can see more of the data from a different angle. Typically what you use is something like a square root to make that transformation, where really what I do is I take my value of x, and rather than leaving the value as x, I would take the square root of x. In other words, take x to the power of 1/2, or just a square root. And that means that if I take all my values of x in my whole data set, if I take the square root of all of those things, then it's a linear transformation. That means that everybody is now changed by having the square root. And so that means you can actually just take your data and take every piece and then remove it to a smaller area. Now the reason you do that is because it removes some of the noise. It makes things less spread out, maybe more concentrated in one specific area. But one thing that's a really good example of putting everything into one specific area is when you take a log transformation. So if you take a log of a number, logs make big numbers small and small numbers bigger. And so what it does is I know that logs themselves are not necessarily linear, but if you're taking a linear transformation, which means that every value in this data set is being taken, you take the log of every value, and then that becomes the new working data set that you're working with, then you get a log transform, and that means the big pieces of data become smaller, and the smaller pieces of data become bigger, and so then you kind of get this, everything's more and more kind of mixed together, and so you can kind of see everything on the same page. And it does help to reduce for what's called skewness, where things are kind of running off the page, parts of your data are trying to get over here, other pieces of data over here, and you don't get a very good feel for what the data is actually doing. You don't see how the data is behaving. So I think this is where we ended up before. I don't mean to waste all your time by repeating all this stuff here, but I think this is an important discussion to have. What we've done here is that these are just regular numbers. You can see that x is equal to 1, 2, 3, and 4, and so on and so forth. But what we're doing is we're taking the y in each of these things is being transformed. So let's see, our equation is x over 52 times 1,000. It's the equation that we had from, here we are, it's right here. This is this equation here, but it's the same equation that we had from it's like the rate equation. And so what we're doing is that's our regular y without any transformation. Now that's the orange line. This orange line just basically takes off and goes straight up like a jet, and it never comes back. Now, you don't really get an idea about if you wanted to kind of see how these lines change in time here. This just looks like it goes straight up, but it moves up so quickly that any other points that you may have on in your data become dwarfed. And so these other lines that we see here are kind of left behind. Now, if we transform these things here, so if I take my data that I was working with, my y, and I transform these things, then that means that now I can kind of get an idea about kind of a trend that I can actually see things and compare things with each other. So here, the blue, I can see the square root of y. This is the orange, which is the cube root of y, and I'm looking at the log of y. And that's the yellow. And so the idea now is that I can actually look at different pieces of data and compare them, because otherwise, if I'm trying to compare these data sets, I can't, because the difference between the maxes of each of these data sets is so great that in order for my graphing function to plot everything, I have to put everything that has a smaller number packed in at the very, very bottom, and everything that's huge goes really, really high up here. And so this makes me think that my values for my other equations, everything that's not orange here, are tiny. But actually that's not the case. I just can't compare them. But when I transform things, then I actually can compare things quite easily. So this is kind of how you can. This is what you can. In science here, they tend to do a lot of transformations to allow us to kind of see different plots and see how things change. You can take, for instance, these are different plots. I think the data is all the same in each of these plots, but they're taking square roots, they're taking 1 over that value, they're taking the log of that value, but each value is being treated the same. And then you just plot those values exactly as you see them. If you take every single piece of the data set and you treat them all the same way, in other words, you take every x, or in this case every y, which is in the upper left, which is the metal diff, or I guess the square root response. But if you take every y here and you treat it exactly the same by running it through some mathematical equation, then you get these new lines that you can look at, and sometimes those new lines are more revealing than what you see before. Anyhow, so there's that. And so this is really what we're doing here. We're looking to show you like how this transformation works. I mean, this is all transformation, but to show you how they're working here, I'm going to look at the 50s, the 60s, and the 70s, and I'm not going to use any transformation of my data. And then we can see kind of like we'll see that we can't really compare things. But this is the I mean, we can compare, but it's not a very accurate comparison, I claim. So we're going to be basically creating 3 different bars to look at from the 50s, 60s, and 70s. And so to do that, I'm going to be using this data from CaliFocus, or California data. I'm basically going to be taking the data, each row here, I'm going to be pulling out these years. So that means, for instance, the data actually has a year column where you have 1960s, 70s, and 80s. And then I'm going to be taking that information and actually putting it into a bar chart, which is all this. And so I get this. This is without my transformation. So it looks like 1970s is really, really small, 1950s is huge, and 1960s is the biggest. Now, if I use the transformation, which is a square root transformation, where all I've done, the only difference in my code is I've just taken my y, and I've taken that, and now I've equaled, I say that y is now equal to the square root of count, whereas before, y was equal to the count. In other words, I'm just now taking the square root of this value here. Then I get a value, or I get these bar chart, or this histogram, where I'm actually able to kind of get a better comparison of the size between these things. It's easier to get comparisons because now everything is more or less on the same page. So now, I mean, here I know that this looks like 1970s is tiny and makes it look like we don't have to worry about we don't have to worry about too much here. But actually, though, it's more realistic to look at this when you have a transformation here, because now you can see that the data does kind of conform to the same kind of playing field, where you can actually get a better kind of, you're able to check things on them or compare them on the same kind of on the same playing field. Essentially, I don't know if I can say that. But the thing is, though, that when we're looking at these things on the same playing field, we're looking at the same scale, I guess you will. In 1950s and 1960s, we see that there's a change between these bar graphs. So this is really where things begin to get kind of interesting. When you're doing your analysis project, you're looking to see kind of that there is a change, and this suggests that there is a change. And this change is saying that in 1950s to 1960s, the cases went up. It went up before it went down. So in other words, in 1950s, things got worse, and then they began getting better when vaccines came in. Now, maybe we're seeing this with the coronavirus, where we're in this, this second, third wave, wherever we are, where we see another spike going straight up, and then things were going to drop off and go down. And so maybe that's where we are right now. And so we ask ourselves, like, how is it that, for instance, we have this, why did things from the 1950s go up to 1960s? Well, remember that this is data analytics, and it doesn't tell us anything about what's going on. It just says that there is a difference, but it doesn't give us any explanation about why that is. And so this is not part of your lab. I'm just venturing out to try and explain this. And so when you are doing your lab or your project or something, where you're trying to explain the results that you have, what you're trying to do is you're trying to go through and figure out, like, well, how do I explain how these results from 50s went up to the 1960s? And so I'm going to make a stab at this and say that here's some other information that I found. And of course, you always have to go to the literature and find more information. But this is information that was saying that in the 1950s to 2050, or sorry, to 2050, they're saying that people are moving out of country dwellings and moving into more urban. They're leaving rural areas and going to more urban areas. Urban and rural populations between 1950s and 2050. Of course, we're not at 2050 yet. but they're just saying that based upon the trends of the data, these researchers, which you can find down at this link here, are saying that people are less likely to be living in countries and more likely to be living in urban areas, starting from the 1950s, going up to the 1960s, 70s, 80s, 90s, and so on. So going back to these numbers here, my argument is saying that I'm looking at these graphs here where people are saying that where these researchers are saying that people are leaving rural areas and moving into urban areas. I'm going to say that that's at the same time, leading up to the 1960s, that's really going to how I'm going to explain this difference here. I'm saying that people, when they left urban areas and they were living closer to each other and maybe in smaller living quarters, smaller buildings, perhaps, where they had more people packed in together. Everybody's sharing the same air. There's less social distancing. I'm saying that that's perhaps how these cases went up, because more and more people now are living together in towns and megalopolis type situations. There's more and more people living together, whereas before 1950s, according to this data, notice what I'm doing here. I'm saying according to this data. I'm not saying I think, because if I say I think, then everyone's like, oh yeah, well I think not. I think that you're wrong, and then we have this argument that can't be won. But you can win this argument here by saying according to this data, and therefore they're not picking holes in you, but they're saying that your data is wrong. Therefore, your credibility is not at stake here, but rather the credibility of the data, which is actually that's easier damage to repair than if someone says that you're a bad researcher because you think the wrong things. That's terrible if someone says that to you. But I'm saying that according to this data, they're saying that people left towns in the 50s, or left their country rural areas and moved into towns and urban areas in the 50s and 60s, making this kind of situation here. People were more close together. The virus had more, had more options of being passed on to other people. And so that's how I'm going to explain that the 1960s was a worse year in terms of cases than 1950s. And then, of course, 1970s, I'm going to explain that was as a result of the vaccine. And so you have to have, when you're putting together a project, you have to have some kind of explanation. But notice, though, that this explanation, all of this stuff here, does not come from this graph. The graph only told me that there was something going on here. There was something happening, but I wasn't sure what it was. And so I had to go then back to the literature or back somewhere else and find some possible explanation. Now, whether this explanation is correct is something else. Who knows? Maybe it's not correct at all. That could be. And we should always be thinking that maybe we're wrong. Maybe we are the first people to ever see this stuff, and we could be wrong. And you have to be willing to kind of accept the humility of saying, I was wrong. And maybe, for instance, you need to go back and redo this analysis. But the thing is, though, that you always have to keep your eyes open and look for some way of explaining your data, because after a while, when you see this isn't an explanation of your data. It just says that something did happen, but you have no idea what that is. When I took this class for the very first time, my data analytics teacher was an astronomer, and he spent many of his evenings like looking through his telescope, as long as they were clear nights, looking through his telescope, trying to see things in the heavens and kind of see distant things. And he'd be reading all these papers about distant black holes and explosions and quasars and things. And he said that he was turned to data analytics because he liked the idea that he could see a blip on his screen and know that something had happened, but then he turned to his telescope and his and other literature to try and figure out what it was to explain that thing. And for him, that was like excitement. That was the exciting piece of the astronomy, trying to figure out what caused that blip of radiation in the sky, what caused this, what caused that. And so that's really what used to get him excited. And so data analytics is exactly that story, where you see this change in your data, and then you have to go back and figure out how to explain that change, what happened. And so here, I'm saying that people began to migrate to populated and urban areas leading up to the 60s, which made it easy for the virus to spread, which seems to be okay, but I could be wrong. It may not be that at all. It could be wrong. The next thing is histograms, I wanted to just to show you like how you can put some code together to make a whole bunch of histograms to kind of like compare the state of California here by the years the 20s, the 30s, the 40s, the 50s, 60s, and 70s, and onwards. And really what you have to do is you have to use this code here where you are creating what's called blocks. These, I just call them here year blocks. But each block represents a chunk of the data from the set where the data has been cut up between the year 1920 and 1929, or here's 1930 to 1939, all the way up to 1970 to 1979, and then onwards, where the year is greater than 1980s. But each time I'm doing this, I'm creating this variable, if you will, which is kind of your block here, which is what I'm going to be using to actually plot. And so now what I'm going to be doing is these are called my year blocks. Let's see, yeah, these are year blocks. I think they're already in there. But what I'm going to be doing is I'm actually going to be throwing those counts into my year block, or my histogram. And so here what I see is I have the 1920s, 1930s, 40s, 50s, 60s, 70s, 80s. These are all the counts of the ailment. In other words, this graph that we see here, histograms by cases, this graph should be exactly the same information, although different, as this graph here. It's the same thing. You should see that trend. But now, this is like, you're not looking at this as a scatter plot, but you're looking at it as a histogram. And I would recommend actually that when you're publishing your data and data analytics, that you might use both histograms and scatter plots. And the reason why you do that is because the histogram is accessible data to many, many more people than I'd say that scatter plots are. Sometimes when people see scatter plots, they become kind of frozen, perhaps. They just don't know how to read it very well. There's so many points they don't see the actual overall trend. But if you see a histogram, this makes it very easy for you to actually to pick out in the text and start talking about, even though you've shown the scatter plot. I try and use both in some of my works, just so that I'm able to kind of hit both types of people. There's some people who like bars and some people who like points, and so I like to throw both of these together. But I'm not actually just putting out two graphs. I try and put these into the text in a different way so that it doesn't look like I'm repeating myself. Anyway, but this is nice because I get some color, and so I can kind of like see. I can compare the years according to different colors. One thing that I'd like to say here, which I try to avoid, but I really couldn't, is I don't like putting green and red in the same plots, just because there's so many people who are colorblind who can't see greens and reds. But in this case, I didn't make any changes. I just let it go. Here we're using a transformation where I'm using a square root of count. And you can see that the same code, when I'm using the transformation, you can actually see now that you're able to compare each of these years on a more even keel, or on the same scale than otherwise. And so now you can actually kind of get an idea about, the smaller numbers kind of creep up, the bigger numbers kind of creep down, and you can kind of get a better comparison going across. And here's the code that makes all of that possible. You can just run these things through. So go ahead and try this code out. You have this code available to you in these slides, and so you can use them to create your very own. You could add this to your very own research projects. And I think though that you'll have to modify things here, but I think that it's a very standard code that many people would use when they're creating histograms where you're showing a progression over time. So anyway, you have that. And if you wanted to just like put all the states in here, which you can if you want, this is actually kind of hard to see. I don't recommend doing this. In fact, I put this in here just to kind of give you an idea that you can show all the states, but when you have so many states as we do, you find that it's actually kind of difficult to differentiate the different colors. And so you might have you might want to take a plot like this and maybe break it up over. If you want to show all the states, maybe not. Maybe show the states in a different way, because here I'm looking at Nevada. It's actually kind of difficult to see what's going on my screen. I just see basically a green point, but I don't see anything else. And so you have to be careful about how many of these histograms you actually put in on the same canvas, because otherwise it makes it very difficult to see. Anyway, I leave that entirely in your hands. You now have this code, and so I invite you to play around with it and see what's going on. But really, though, that was kind of what the lab I was expecting to look like. Now, of course, I'm still grading everything here. I'm not saying that your lab wasn't worth anything if it didn't look like this, but I wanted to see in your lab, I wanted to see that there was this, what was it, this plot right here. That plot was absolutely essential. I wanted to see that was, or something like that, to make me know that the vaccine was having some effect on the cases, that the cases were coming down after the vaccine was being given out. So anyway, that was really the criteria. Are there any questions? I hate to keep blabbering on like this, but are there any questions over this at all? Is there any questions here? Well, tell you what. If you do have questions, please feel free to let me know. And I'll be very glad to take any questions you may have. Now, I wanted to move into the next thing here. You have in your class docs repository, we have some stuff for today. I wanted to go over the exam. So what we're doing is we have the exam that's given out on Thursday. And Thursday at class time, which is 11:10, which means that we're not actually having a formal meeting of class the next class this week. So that means that on Thursday of this week, I'm just going to be giving out the exam too, and there's no formal meeting. Now, you can take the exam whenever you want. You can take it at 11:10, or you can take it at 11:10 a.m., or you can take it at 11:10 p.m., or whenever you want. The test is actually due by 3 p.m. on Friday the following day. So you have more than 24 hours to take this test. It is not going to take you 24 hours to take the test. I can assure you, don't worry about that. It's not going to take you 24 hours to take the test. You can have as much time as you want to take this test. I mean, I hope that you're not going to spend, that you will not spend all this time taking the test. I hope it's not that kind of test. But you can take it whenever you want. But I will say though that please, whenever you do take it, make sure that you don't take it like at, if it's due on Friday the 20th by 3, don't sit down at 2:50 p.m. on Friday the 20th. And start taking your tests, because you won't have time. You need to have at least, I would say, give yourself at least 2 hours, just on the safe side, just 2 hours. Although you may not use it, probably won't use it, but give yourself at least that much time all together so that you can take your test. Now, the reason why I'm saying this is due at 3 o'clock, and by the way, if you have a good reason why 3 o'clock is too soon for you, then get in contact and we can talk about an extension of this, but you have to let me know before the test begins. But I want you to come to lab on Friday, because on Friday's lab, I want to talk to you about the project assignments. Now, we haven't discussed that yet, but the project assignment is, we're not having in this class a final exam. I don't like exams. There's no final exam. Instead, I want to give you the opportunity to use your own skill and your own intelligence, your own whatever you want, your own abilities, to go after a research project and to solve something about that research project, to provide some analysis behind that research project. All will be made clear, but it's going to be basically an open project where you can choose the data and the analysis technique and your questions that you're answering. You can choose all of these things, and that is what we're going to be talking about on Friday. I anticipate this to be a conversation of about 10 minutes. So it's just going to be that. I'll give you the assignment at that time, but please do come on Friday to our lab. I'm not going to be giving out a new lab, but I am going to be talking about this project assignment here, and so please do come to that if you can. If you cannot come to that, then well, let me know. We'll find some other way. I'll probably have to release a video of that lab so that you can see it. So anyway, the details from the exam 2 are going to be, you'll have 10 to 15 questions of multiple choice and short essay. These are probably matching there too. You're going to be having, it's basically the same thing that we had last time, the same format as lab 1. Your lab material will not be on the lab, or sorry, your lab material will not be on the exam. You do not need your labs to be successful on the exam. You're basically going to be writing in some basic R code in RStudio and answering some questions based upon your code. It's going to be all, the material that I'm covering here is all material since exam 1. And of course, it's open notes, open book, open everything, open brain. Um, so you can, I mean, it's a take home, so you can use all this stuff at home. You have to work by yourself though, and you are bound by the Allegheny College Student Honor Code. So please um, adhere that you follow those guidelines. Yes, sir.
Everything after.
Yeah, correlations, t-tests, linear models, the stuff that we've, the juicy stuff that we've been covering more recently. But still, I mean, you can use your slides, and it's all right there. There's code in your slides that may assist. But it's all the stuff from exam one. So it's like everything after the, I guess some of the I guess when we began talking about the like basic statistics. I think our last test was in October sometime. Is that right? October 20th or something? Is that right? I'll just find out. What exactly was the date for that? You can click on this over here. You go to classes. You can go to data analytics, and I move to planning your time. I haven't updated this calendar. I do apologize about that. We had during week 6. That was our first exam here. So that was on the 8th of October. So don't worry. When you see the exam, though, I mean, you'll recognize these pieces, and you'll be able to find everything in the actual labs. Oh, sorry, the actual not the labs. You'll be able to find everything in the slides, and so that should be able to help you get on, help you be successful for your test. But yes, the question was, we're going back to exam 1 for all the material. Yes, that's where the questions are coming from, but probably more recently than that. I haven't completely finished actually building this exam yet, but you'll find this on Sakai. It'll be there. It'll drop at exactly 11:10 on Thursday. So there's no class. Sorry. Now, what I wanted to do is I wanted to give you something to kind of work with to give you an idea about, kind of get you ready for the exam. And so I have a practical for you, practical 3. And what I want you to do is to use this repository for your previous practical, and I want you to go to your class docs repository and to copy the directory. Here, let me just show you. So I'm going to go to my class docs repository here, and I keep them in repo 2020 fall CS 301 class docs, and I go into my lessons. I go into 12, for instance, week 12. I should change that name here. There's this repository here called 03, or this directory in this repository called 03 practical with this file here. What I want you to do is, I want you to actually copy this whole directory. This is a directory here, but this directory here, copy that into where you find the repository you get to when you click on that link. Just copy it in there. And that's how I'm going, and then I want you to submit from there. So once you copy it over, start working on it in here, and then when you save your settings and you push them, then I can see them on my end. But copy your work into this directory, whatever this directory is that you get, and then push it. So really it's this. And to grade everything, I'm going to be looking at this file here, this markdown file. These work individually or in a group. I guess that's very, very open. If you do work in a group, please be sure to add the names of the people that you worked with. It just helps me to grade. And please submit everything here by Thursday, the 19th, by 12, which is actually next class at noon. So going back to this, let me just go back to this, the actual document I want you to work on for the practical. Let's go in here, and I'll show you. I'll just use Vim here to go through the file. But here are some questions I want you to go through, and that is that you're going to be doing some basic just analysis where you have to type in some code. Now, if you look at this, this is a markdown file. And so you'll see that there are these little things here. These little things here, when you look at your code, when you look at this file in GitHub, you'll find that there's a gray box surrounding this code. So anything that's inside these little quotes here is actual code that you're going to be working with. That's just a markdown, syntax. But you're going to be using these pieces of code and then kind of going through and following questions and answering those questions. And so, for instance, you'll be running this thing through, and I'm not going to tell you everything here, but wherever you see this to-do, please go through and remove that to-do and then put your answer in its place. You'll be building working with some data sets, building models, plotting things out, and just answer your questions if you will. And certainly, if you're over here, for instance, you're creating a plot, but actually I don't want to see the plot. I want your code here so that I can run your code at home. Anyway, I'll stop right here. Please have your work done by the, what did I say here? By next class at noon. That's really all I had for today. Are there any questions at all? We can adjourn if you'd like, and then you can start working on this, or you can just look at me staring straight into the camera until the end of class. What would you like to do? Rather than just staring at the camera until the end of class? Anyway, I think that if you spend some time working with this should get you in good shape for the test. And I think you should be good to go. You've got some juicy stuff in there. You're plotting things. You're looking at data. You have some models going on there. You're determining whether you should accept or reject a null hypothesis. It's just action packed.